think of an undirected edge as a two-way directed edge, right? So either way is fine. We can also have an undirected edge and represent our adjacency matrix like that as well. That's, but we would need to have two entries for an undirected edge. Okay. So, okay. So the edges that are actually part of the DFS search process are called tree edges. So edge u comma v is a tree edge if v is discovered while we are exploring the edge u comma v, right? Then we have forward edges. Forward edges are edges that start from a node and goes to a child node, but that particular node did not get visited, or sorry, did not get, that particular edge was not used to explore the child node. So for example, a forward edge could be, so a tree edge for this particular graph here is basically all the edges between A and B, from B to C and then B to D, right? Now, a forward edge is basically any edge that goes from a parent node to a child node, but that particular edge was not used to discover D. So in this particular scenario, we are using B to discover D, and that is why we did not care about this particular edge, and that particular edge is called a forward edge. Then we also have backward edges, where a particular child node has a direct connection back to the parent node. Here, child and parent basically comes from the fact from our pre-visit and post-visit numbers. So if we have a higher pre-visit number, that is essentially considered as a parent node, and then we have a child, right? So then when we have back edges, it basically means that we are not using C to explore A, but instead we used A to explore C. So a back edge could be an edge connecting back to A, but it is not part of the DFS forest. And then we have cross edges that are basically connections between siblings. So basically nodes that are neither descendants nor ancestors. And therefore it is basically connecting two components that are completely explored, and are not part of the tree itself. So these are the four types of edges that we come across when we are talking about DFS in directed graphs. And the next time we are going to talk about these pre-values and these pre-visit values and these post-visit values in more detail later. And what properties do they have, and what can we infer from them, and other things. So
that graph you showed previously, none of those dotted edges are actual connections of the original graph, right? You really just have those solid edges, and then those that back, forward, and cross are just
no. No. Okay. So this entire graph is including the dotted edges and the bold edges. The bold edges represent the edges that DFS used to explore this graph. The dotted edges represent edges that are part of the graph, but DFS did not use them to explore it.
Oh, okay, but every single one of those edges exists in the original graph, right?
Yes. So essentially we have this particular graph with these edges as well, right? So I'm going to draw them in yellow, right? Now let's start with A, and I discover B. From B, I need to again explore from B. So I use B to explore C first, and then I come back to B, and then I explore D, right? And I'm done. Now these yellow edges are also part of the graph, but I'm only using these middle edges here to discover my entire graph. These dotted edges are not part of my discovery or exploration process, although they belong to the graph. But since they have basically, they are connecting nodes that are already visited, I did not need to look at them. And that those are what those dotted edges represent. And the direction those dotted edges go are basically representing whether they are a forward edge or a back edge or a cross edge. On the other hand, tree edges are essentially edges that we are using to actually explore the tree, or they explore the graph. Does that make sense?
I think, can you also draw a line from D to A and call that a back edge as well?
Yes, you can have a line from D to A, and let's say that this was in the graph, and let's say that it is from D to A. I can't draw an arrow here, but So this goes that away. Right, we can have a line from D to A, and that would be considered as a back edge, but not a tree edge. And this would be the entire graph. Still confused? Want me to give you an example for this thing? Okay.
I guess I just want to clarify that
Mm-hmm.
we have
Okay,
both
so
back and forward edges.
yeah.
on
Okay. Okay.
back.
Let me use this old example here. Let's bring up a notepad, and let's say that we used. So we start off from 1. So 1 is visited, and we used the edge 1, 2 to visit number 2, right? And then we go to 2, and then we use the edge 2, 4 to visit node 4. And then we come back to 1, and then essentially we go to node number 3 using the edge. So we come back to 1, and we use node edge 1, 3 to get to node 3. And then once we get to 3, we are done, right? So in this case, we basically used, let's see, we have a color. So in this case, we basically used this edge to go to 2. From 2, we went here. And then once we went to number 4, we came back to 1, and then we used this edge to go to number 3. Does this sort of hand-drawn example make sense till now?
So we have a forward edge from 1 to 4 and then a back edge from 4 to 1, correct?
No. Okay. So we have edges from 1 to 2. So this red is sort of an arrow that points there. And from 2 to 4, and then from 4 to 1, and from 1 to 3. Okay, give me a second. Let me write up the adjacency list first for this particular. Okay, so the adjacency list for this particular graph is from 1, we have 2 and 3, right? So we have 2, then 3, right? 2, we have only 4. From 3, I have nothing. And from 4, I have a connection to 1, right? Where we have initial is the from value, and then we have the 2 vertices, right? So first things first, does everyone agree that this is the adjacency list for this particular graph? No forward edge in this. There is no, Vasireti, you're exactly correct. There is no forward edge in this example. Can you tell me what type of edge is present in this example? A back edge, backward edge, exactly. Okay, so if you understand that this is an adjacency list to this graph, now let's evaluate how a DFS would work on this particular graph. So let's say that this was the DFS process where I start off from node 1 here, and then I basically use node, this particular edge 1, 2 to get to node 2, right? From node 2, I will explore node 2 now. So from node 2, I basically use this particular edge 2, 4 to get to 4. From node 4, I am trying to explore 1, but it is already explored. So I come back directly to 2, then I come back to 1. And from 1, I am now exploring node 3 using the edge 1 and 3. And I get to 3. And once I get to 3, I know I am done because there are no other nodes here or no other vertices available in this entire list. So does everyone understand how we explored it using DFS in this example? Yes. And so do you now understand how, so this particular graph, as Brian says, does not have, no, this particular graph, as Vasireddy says, does not have a forward edge, and this particular graph, as Brian says, only has a backward edge. So first things first, I want you guys to tell me, or one of you to tell me, what are my tree edges for this particular graph? Where tree edges, let me bring that up. Where tree edges are the edges that are actually part of the DFS search procedure. So we have, yes, 1, 2, 2, 4, and 1, 3. Those are my tree edges. There are no forward edges in this graph because there is no node that goes from the child, that goes from the parent node that was 1 or 2 and that order, where the order was 1, 2, 4, and 3. There is no node that goes from 2 to 1 or 4 to 2 or 1 or 3 to 4 or 3 to 2 or 3 to 1. Right? There are no edges that are connecting back, sorry, the other way, my bad. There are no edges that connect directly from one to the other vertices. We are talking about forward edges. So a forward edges, if there was a connection from one, let me bring out another color. Okay, so let's say that we had a connection from 1. Let's say that we had a connection from 1 to 4. Right? If we had a connection from 1 to 4, this would be an example of a forward edge, where we did not use this particular edge to discover the node 4. But there is an edge from the parent node to the child node. Does everyone understand how the thick black edge is a forward edge?
Yes. Is the forward and back edge, is this specifically for directed graphs?
Yes.
Oh, okay. So because that arrow is pointing back from 4 to 1, that's considered a back, because 1 is its ancestor and it's pointing back to it. Okay, got it.
Right, and the forward edge is basically, since 1 is an ancestor, if there is an edge from 1 to 4, that becomes a forward edge. But since we have an edge from 4 to 1 and we are not using that edge to explore this entire graph, that is considered as a back edge. So all the nodes, all the edges that we require to explore this particular graph in DFS are considered tree edges. All the other edges are unexplored edges, but explored vertices, but unexplored edges, where we have the forward edges, where we have ancestor to child nodes, where we have back edges, where we have child to ancestor nodes, and then we have cross edges, which are usually basically sibling connections, or if there was a connection between 3 and 4, that would be a cross edge, because both of them are already explored, so we don't need to explore either. Does that make sense now?
Yep.
Any other questions? Yes, Taha, there will be a quiz on Thursday. We will, the quiz syllabus will be everything we have covered so far. Oh, right, that is a symmetric matrix. Oh, okay. No, I also, my bad. So I accidentally called that particular matrix as a diagonal matrix because that is what came to my mind. But essentially, an adjacency matrix, when we have undirected edges, and I'll talk about this in more detail later, but remember that I talked about how the top part of the diagonal looks the same as the bottom half of the diagonal, but the mirror of it.